going to present a topic matrix multiplication on multiprocessor and multi-computers, which is nothing but a MIMD, multiple instruction and multiple data streams. So which is a multiple processor and this is a multiple computers. Each processor share the shared memory, that is a multiple processor. Multi-computers, it has its own memory, local memory, and also it shares the data with the other processor by means of a interconnection memory. So how this can be done? By means of a row oriented and by means of a column oriented. The matrix C, it consisting of the processor which is arranged in the row oriented, and the matrix C which has arranged the processor in a column oriented can be represented by means of a n rows by p processor equal to n by p, that is rows per processor, number of rows per processor, and m columns by p processor, which is a n by p columns per processor, total number of processor per column. The same matrix multiplication can be represented sequentially by means of an algorithm consisting of two loops for the which stands as an index for the elements of the A and B matrices, and the loop K which does this multiplication by normal concept of this multiplication Aik plus Bkij. So we are going to parallelizing this loop here. It is parallelizing this ith loop, that is what we are going to do this, that is doing this Kij in a parallel manner. The same algorithms for multi-computers can be done by two methods. One is a row column oriented algorithm and another is a block oriented algorithm. First, partition the matrix A into rows and B into columns. N is a power of 2, and executing the algorithm on n processor hypercube, we have to parallelize the outer loop I, and all parallel processor access column 0 of B, then column 1 of B, etc. In case of multiprocessor, too much contention for the same memory bank is occurred, then we call it as a hotspot. So eliminate this contention for shared resources by changing a temporal order of data access. So change the order in which the algorithm computes the elements of each row of C. Processes are arranged as a ring. After each process has used its current column of B, it fetches the next column of B from its successor on the ring. So which can be represented by means of a diagram, that is 4 processes to multiply matrices A and matrices B. So whose iterations, after these iterations, this P, P2, P3, P4 are arranged in such a manner that does represent by means of a bar diagram. There is a by means of a bar colored in green. This is over third iteration, and fourth iteration is the last iteration. We get the result. So generalizing this row column oriented algorithm, first multiplying L into M and M into N matrices on P processor where P less than L and P less than N. Assuming L and N are integer multiples of P, every processor begins with the L by P rows of A and N by P columns of B and multiplies the I by P into M submatrix of A with the M into N by P submatrix of B, producing A into L by P into N by P submatrix of the product matrix. Then every processor passes its piece of B to its successor processor. After P's iteration, each processor has multiplied its piece of A with every piece of P. So that is L by P into N section of the product matrix. The total number of computer system steps is LMN by P. Next, the same matrix multiplication for multi-computers by using a block-oriented algorithm. Here, to maximize the number of multiplications performed per iterations, okay, whereas the previous case there is a limited number of multiplications, here we are going to maximize the number of multiplications. Actually, this block-oriented multiplication algorithm is explained in Unit 3. Right, so let us see an overview how this block-oriented algorithm done for this multiplication of matrices over multi-computers. Multiplying L into M matrix A by M into N matrix B, and N and N these are multiples of root P, whereas P is the even power of M. As a two-dimensional mesh with the wraparound connections, each processor L by root P, M by root P subsection of A, M by root P and N by root P subsection of B. Here the block matrix multiplications performed analogously to scalar matrix multiplication. Algorithms previously used on two-dimensional mesh of processor with the staggering technique. The same staggering technique is used to position the blocks of A and B so that every processor multiplies two submatrices each and every iterations. Phase 1. Staggering the block submatrices of matrix A is done in both the directions, left and right. And then staggering the block submatrices of matrix B is done in both directions, up and down. So it is represented as A of 1,3 and A of 3,2. From P of 1,2's point of view, C12 after doing this left and right, this is left movement and right, that is up movement, we get C of 1,2 equal to A13 into B32 plus A10 into B02 plus A1, 1 into B1, 2 plus A1, 2 into B1, 2. So the first part says that during the left movements, and right part says that during the upward direction. So that is represented means of a diagram here. So the total communication time for this algorithm is sending and receiving a message as a message latency lambda plus message transmission time beta, number of values sent. So that's all about this matrix multiplications on multiprocessor and multi-computers.